Have you ever wondered what it's like to break the sound barrier? Let's dive into this high-speed mystery. When we think about the sound barrier, it's easy to visualize it as an invisible wall waiting to be shattered by a brave pilot in a supersonic jet. But in reality, the sound barrier is not a physical barrier at all. It's a sudden increase in aerodynamic drag and other effects that an aircraft experiences as it approaches the speed of sound, which is about 762 miles per hour at sea level. Now, imagine an aircraft accelerating towards this speed. As it nears the sound barrier, the air in front of it starts to compress, creating a wall of compressed air. This is because the aircraft is trying to push through the air faster than the air can move out of its way. This is what creates the phenomenon we call the sound barrier. But what happens when an aircraft actually exceeds the speed of sound and breaks this barrier? Well, it's like pushing through that invisible wall of sound energy and coming out on the other side. The aircraft generates pressure waves that combine to form shock waves. These shock waves move through the air like ripples on a pond after a stone is thrown into it. And you know what's interesting about these shock waves? They are responsible for the phenomenon we know as a sonic boom. When an aircraft flies faster than the speed of sound, it's actually outrunning the sound waves it's producing. So when these shock waves reach us on the ground, we hear them as a sudden change in pressure, a sonic boom. So essentially, breaking the sound barrier is like pushing through an invisible wall of sound energy and coming out on the other side. It's an exhilarating blend of physics, speed, and raw power. It's not just about going faster, but about understanding and harnessing the forces at play when we venture into the realm of supersonic flight. Now, let's take a look at one of the most iconic supersonic aircraft, the Concorde. The Concorde was a symbol of innovation, a marvel of engineering that was capable of flying at over twice the speed of sound. That's faster than a rifle bullet, folks. It cruised at altitudes where the sky appears dark and the curvature of the Earth can be seen. With this exceptional speed, the Concorde slashed transatlantic flight times in half, making it possible to have breakfast in New York and lunch in London. However, the Concorde was not just about speed. It was designed with a slender delta wing configuration that allowed it to maintain its aerodynamic efficiency across a wide range of speeds. Its distinctive droop nose was a solution to the problem of providing good visibility for pilots during takeoff and landing, while still maintaining the aerodynamic profile needed for supersonic flight. But supersonic flight is not limited to commercial aviation. It has also been a significant aspect of military aviation. Take, for example, the F-22 Raptor, an American stealth tactical fighter aircraft designed to perform air superiority missions. Its top speed is estimated to be around 1.5 times the speed of sound. Similarly, Russia's MiG-31, also known as the Foxhound, is one of the fastest combat jets in the world. It can reach an impressive speed of almost 3 times the speed of sound. These supersonic aircraft not only rewrote the rules of speed, but also revolutionized our understanding of flight. They pushed the boundaries of what was thought possible, challenged engineers to solve complex problems, and captivated the public with the allure of supersonic travel. The Concorde, the F-22 Raptor, the MiG-31, and others like them are all testaments to mankind's unyielding spirit of exploration and the desire to push the limits of our world. Designing an aircraft that can withstand the rigors of supersonic flight is no easy task. It's akin to creating a masterpiece that not only looks good, but also performs exceptionally under extreme conditions. One of the major challenges is dealing with the intense heat generated by air friction. As an aircraft accelerates to supersonic speeds, the air molecules around the aircraft can't move out of the way fast enough. This creates a compression wave that heats the air and, in turn, the aircraft's surface. Think of it like this. If you've ever quickly rubbed your hands together, you'll notice they get warm. That's friction. Now imagine that on a much larger and faster scale. The aircraft must be built with materials that can withstand this intense heat, yet are light enough not to hinder the aircraft's performance. Then we have the challenge of maintaining stability. As the aircraft moves from subsonic to supersonic speeds, the center of pressure, that is the point where the total sum of a pressure field acts on a body, causing a force to act through that point, shifts rearward. This can cause the aircraft to pitch up, potentially leading to a loss of control. To counteract this, supersonic aircraft are often designed with a swept-back or delta-wing configuration, which helps to stabilize the aircraft as it exceeds the speed of sound. Lastly, there's the sonic boom to consider. This loud, thunder-like sound is a byproduct of those shock waves we discussed earlier. It can be quite disruptive, especially if the aircraft is flying over populated areas. Managing the sonic boom is a delicate task. Engineers use clever design techniques, like shaping the aircraft in a way that the shock waves don't coalesce into a single loud boom, but rather into a series of smaller booms that are less disruptive. Designing for supersonic flight is a complex balancing act, pushing the boundaries of both engineering and physics. It's a testament to human ingenuity and the relentless pursuit of pushing boundaries. Despite the groundbreaking advancements, supersonic flight still presents significant challenges. One of the major hurdles is the environmental impact. Supersonic jets consume a lot more fuel than subsonic planes, leading to higher carbon emissions. Noise pollution is another issue. Sonic booms, the loud thunder-like sounds that occur when aircraft exceed the speed of sound, can be disruptive and are a major reason why supersonic flight over land is heavily regulated or even banned in many places. In addition to environmental and noise concerns, the high operating costs of supersonic aircraft pose a significant challenge. From fuel consumption to maintenance, the costs associated with supersonic flight are considerably higher than those of conventional aircraft. This is a key factor that has kept supersonic flight from becoming mainstream in commercial aviation. However, the future of supersonic flight holds great promise. Technological advancements are paving the way for more efficient and quieter supersonic aircraft. Innovative designs are being explored to reduce the sonic boom, such as NASA's X-59 quiet supersonic technology aircraft, which aims to produce a sound no louder than a car door closing. Furthermore, research is underway to develop more fuel-efficient engines and materials that can withstand the intense heat generated at supersonic speeds. Companies like Boom Supersonic are working on next-generation supersonic passenger aircraft that promise to be more efficient and affordable. There's also growing interest in the use of supersonic flight for space tourism. Companies like Virgin Galactic and SpaceX are exploring the potential of supersonic and even hypersonic travel for short suborbital flights that could offer passengers a unique experience of space. Despite the challenges, the desire to travel faster and further continues to drive innovation in supersonic flight. As we continue to innovate and push the boundaries of speed, the future of supersonic flight holds great promise. Supersonic flight is a testament to human ingenuity and the desire to push the boundaries of what's possible. As we have seen, breaking the sound barrier is not just about going faster. It's about understanding and overcoming the aerodynamic effects that come into play as we approach the speed of sound. We've delved into the fascinating phenomenon of shock waves, those sudden changes in pressure that can produce sonic booms. We've also seen how these can pose significant challenges, not only for the aircraft and its passengers, but also for people on the ground. We've taken a flight back in time with the Concorde, the most iconic supersonic passenger aircraft. Traveling at over twice the speed of sound, the Concorde revolutionized transatlantic travel. But it wasn't alone. We've also touched on some of the incredible military aircraft like the F-22 Raptor and the MiG-31 that have achieved supersonic speeds. We've grappled with the design challenges that come with high-speed flight. The need for an aircraft to withstand extreme heat, maintain stability under changing forces, and manage the sonic boom are all crucial considerations for engineers and designers. We've also highlighted the current challenges and the future of supersonic flight. While the Concorde no longer graces our skies, the dream of supersonic passenger travel is far from over. Companies are already working on new technologies and designs that could make supersonic flight more accessible and sustainable. In essence, supersonic flight is a fascinating blend of physics, engineering, and design. It's a field that continually pushes the boundaries of speed, challenges our understanding of aerodynamics, and inspires us to reach for the skies. As we reach for the skies, we continue to redefine the limits of speed and design. This journey into the world of supersonic flight shows just how much we have achieved and how much more there is to explore. Until next time, keep exploring and stay curious.